Jai Hind to all. Today, myself Shikha Agarwal, Assistant Professor of IT Department from Ajay Kumar Garg Engineering College. In this lecture, we are going to discuss about a one complex topic of data structure, that is a minimum spanning tree. If I am talking about a minimum spanning tree, before that we should know what is a spanning tree. We know if I am using the word minimum, it means we are talking about the minimum cost of a tree. But we know how we are talking about the spanning tree. So if I'm talking about a spanning tree, we can say, suppose we have a graph G. In the case of graph G, whatever the subsets is possible for the graph G, in which we have to cover all the vertices, and in this case we have to talk about the minimum possible edges of a tree. Then we can say it is called as a spanning tree. And remember one more point, that when we talk about spanning tree, it does not consist any cycles. Remember that it does not consume any cycle, and simultaneously it cannot be disconnected also. So we can talk about the spanning tree. So the proper definition of a spanning tree is that a spanning tree is a subset of a graph G in which we have to cover all the vertices with the minimum possible number of edges, and somewhere it does not consist of any cycle and it cannot be discontinued. So you can see the example. Suppose if I am talking about this graph, in this graph we are having a 3 vertices, that is A, B, C, and with these vertices we are having a 3 edges. So out of that we are able to create the 3 spanning trees in which there is no cycle, and simultaneously in all the 3 cases it consists of all the vertices with the minimum number of edges. Fine. If we found these 3 spanning trees for a one complete graph, so if I am talking about an undirected graph, in the case of complete undirected graph, if we talk about the minimum, how many number of spanning trees we can generate. So in the case of complete undirected graph, we can say we can generate n raised to power n minus 2 number of spanning trees, where we can say n is the number of nodes. Now in the above example you can see, suppose if I am talking about this graph is having a 3 vertices. So how many number of nodes we have? We have 3 nodes. So if we want to calculate the possible spanning trees, so in that case we can use the power, that is 3 means n raised to power n minus 2. So if in that case we have 3 raised to power 3 minus 2, that comes out to be 3 spanning trees. So by default when we generate the normally spanning trees, we are getting the 3 possible cases. Now after that, if we talk about the spanning trees, there are the certain properties of a spanning tree. The following properties we have. First of all, when all the graph G can have more than one spanning tree. As in the previous example you can see, suppose we have this one graph and there are the 3 possible cases. So similarly the first property is that whatever the connected graph G we have, it can have more than one spanning tree. Second is, if I am talking about the spanning tree, all the possible spanning tree of a graph G can have a same number of vertices and edges. All number of vertices and edges is to be same. Second thing, in the case of a spanning tree, it does not consist of any looping or cycle. Second thing, if I am talking about removing any one edge from the spanning tree, it will make a graph disconnected. And if the graph is disconnected, then the spanning tree is called minimal connected. You can see the example. For example, in this spanning tree, if I remove this edge, so it will become A as a separate node, C and B. So now this particular graph is disconnected. If this graph is disconnected, then it is saying to be minimal connected. Second thing, if we want to add a one edge to the spanning tree and create a circuit loop, then the spanning tree is maximally acyclic. For example, in this case, if I am talking about, if I create this line, so somewhere it creates a cycle. From cycle means from where we have begun, we have to come on to that same destination. It means it is called as a maximal acyclic. Now, so if in that case, what is the minimum spanning tree? If suppose the weights is being given in a weighted graph, the minimum spanning tree is that tree in which we are having a minimum weight than all other spanning trees in the graph, in the same graph. So it means we are talking about the minimum spanning tree. In the real world situation, generally these all the things in which the weight is to be measured in the form of distance, time, congestion, traffic load, or any arbitrary value which is being denoted on the edges is called as a weight. Now, when I am talking about the minimum spanning tree, in the case of minimum spanning tree, there are the various algorithms. On the basis of that, we have to calculate the minimum spanning tree of a graph. So the first method or first algorithm is Prim's algorithm. When I am talking about the Prim's algorithm is used to find the shortest or the minimum cost effective spanning tree of the algorithm. Generally, it uses the greedy approach. So if I am talking about the Prim's algorithm, this is also similarly like a Kruskal's algorithm. We will study about one more algorithm, that is a Kruskal's algorithm, in which we are talking about to calculate the shortest path first algorithm. Prim's algorithm in the contrast with the Kruskal's algorithm, in which what happen? In this case, we have to treat all the nodes as a single tree and keeping on adding all the nodes, new nodes to the spanning tree in a given graph. Now, if I am talking about the algorithm in the case of Prim's algorithm, first of all, we have to select the starting vertex. Whatever the conditions we have, suppose we have given this graph. In this graph, first of all, we have to find the starting node. So, for example, if I say S will be a starting node, then after that, we have to repeat the step number 3 and 4 until we are there are fringe vertices, means after that we have to cover all the vertices. First of all, if we select any edge E which is being connecting to the tree vertex and fringe that vertex, that should have a minimum weight. If the particular node is having a 2 adjacent nodes, so we will take a minimum weight node so that we can move from one vertex to the next vertex, and so on. In the last, we have to add the selected edge and the vertex of the minimum spanning tree to the given tree T. And this is the way how you have to generate the Prim's algorithm. Now you can check the method also, you can check the algorithm also. Now if I am talking about its algorithm, first of all we have to generate MST_Prims. It stands for minimum spanning tree by using the Prim's algorithm. G stands for graph, W stands for weight, and in the case of R, we have to denote the wedges. Fine. So first of all, we have to talk about all the vertices. We have to apply the for loop. In the case of U, it belongs to all the vertices of the given graph. After that, what we have to do, we have to put the key values for each and every vertex is to be infinite, so that we can calculate the shortest path of that particular node. And in that case, we have to pi the nil, so that we can maintain the distance of that also. And lastly, whatever the key element that is in first element source node, we have to write at 0. And in the final result, we have to maintain the key. In the case of key Q, we have to write all the vertices one after another while extracting the minimum element from the Q. And we have to work onto the while loop until and unless we get the desired output. So after that, what we have to do, we have to extract the minimum element of the Q, and then we have to adjacent their key values, and we have to apply the relaxation method. Now if I am talking about the priority queue in the case of this element, the minimum complexity what we need to calculate is O E log n, log V. Fine. So this is the way how we need to the complexity also. Let's us discuss one example. Suppose we have to apply the Prim's algorithm on the given graph G. In this case, first of all, remember one thing. If there is a cycle, if there is a parallel edges, so first of all we have to remove the parallel loops and parallel edges. So in this graph you can see C itself has a one loop with the value 1, first thing, and simultaneously A to B and B to A, there are the two edges. So what we have to do, we have to remove all the cycle loops as well as the parallel edges. First of all we will remove the cycle. Then after that we have to remove the parallel edge. We have to remove that parallel edge which is having a maximum weight. So we will remove the 9. Fine. Then after that we will get this graph. After removing all the parallel edges and the loops from the given graph, in this case all the parallel edges and loops is to be least costed, because what we have to do, we have to talk about the minimum spanning tree. So they are least concerned about all these graphs. It's fine. So that is why we have to remove all the loops and parallel edges. In the second step, we have to choose one arbitrary node. Arbitrary node means from where we have to start, or it is also called as a root node or source node. So for example, in this case, if we choose S as a source node or root node, fine. So after choosing that root node, what we have to do, we have to check the rest of the tree depending upon the S as a source node. Now after that we have to check their outgoing edges and we have to select the one edge with the least cost. Or in another way we can say, when I am talking about the root node S, we have to check their adjacent nodes, and whosoever is having a least value, minimum spanning, then we have to consider that edge only. So for example, if I am talking about S is having a two adjacent nodes, that is A and C, and out of that A and C, S to A is having a minimum weight, that is 7. So we have to choose the edge 7. Fine. Then we move to the next node, that is A. Fine. After coming to the A, again we have to repeat that step, that we have to choose the again minimum spanning tree. So in that case, if I'm standing on A, we are having this as a minimum edge and this as a minimum edge, because out of 6 we are having A to C, that is a 3 weight, that is a minimum spanning tree. So we will consider this as a next edge. Fine. Then after that, when once we came on C, now again we have to check their adjacent nodes, and once we check their adjacent nodes, there are adjacent 4 and 3, and out of these 2, which is the minimum spanning tree, that is 3. So we have to move on 3. Fine. Then after that, coming on to the D, again in the case of D we have to check their minimum weights. Now you can see one thing, that in the case of B to T as well as B to D, both the weights are same and both the weights are minimum, right? So what we have to do, we have to take both the edges by using the minimum weights. Now after that we have to either move on T or on B, but if we consider any of the node, in that case we have to consider this edge, that is the weight 5. And if we include this weight, it means it will generate a cycle. So what happened? We will not consider this loop. So that's why this tree is called as a minimum spanning tree, in which you can check that we have covered all the vertices, right? We are having 6 vertices, that is S, A, C, B, D and T. So we have covered all the vertices, and finally we are getting the minimum spanning tree out of all the various combinations, right? Now if you need to calculate the minimum cost of this tree, what will be the cost? Minimum spanning tree cost is equals to the summation of all these edges. So what you have to do? 7 plus 3 plus 3 plus 2 plus 2. So what is the minimum cost of this tree? That comes out to be 7 plus 3 10, 10 plus 3 13, 13 14. So it comes out to be 17. So what is the minimum cost of using this tree? That is called 17. Now after that, what we have to do? We have to consider the one more example, that is called as a Kruskals algorithm. Yes, we know that we have used the Prim's algorithm. Prim's algorithm is a one way to calculate the minimum spanning tree, and Kruskals algorithm is another way to calculate the minimum spanning tree. If I am talking about the Kruskals algorithm is also used to find the minimum spanning tree for a connected weighted graph. But in this algorithm, what we have to do, we have to mainly target of the algorithm is to find the subset of all the edges by using which we can traverse every vertex of the graph. Similarly, in the case of Kruskals algorithm, it also follows a greedy approach, which also finds the optimal solution at every stage instead of focusing on a global optimum. Fine. Now you can check an algorithm also. The algorithm says in the step number 1, first of all what we have to do, whatever the graph is being given, we have to create a forest of each graph in a separated tree form. Fine. Second, we have to create a priority queue that contain all the edges of a graph. And what happen, we have to repeat that step until and unless we reach that the queue is to be empty, so that we can remove all the edges from the key. And finally, if the edge is obtained from step number 4, we have to connect the two different trees and add them to the new tree, combining the two trees, and else otherwise we have to discard that edge which is of no use. Fine. Now you can see the example also, algorithm also. In the case of algorithm, we have to apply the Kruskals algorithm by using the two things only. First of all, we know the graph as well as we know the weights. In this case, we need not to create any as a first node or a root node. But in this case, first of all, we have to create the forest of a tree. Forest means we have to create the separated nodes. Just for example, in the similar graph, we have to create the vertex S, A, B, C, D and T. So this tree becomes a forest tree. Now by using this forest tree, we have to make the minimum spanning tree. Then initially what we have to do, we have to put in an A as a phi, in which that we have to make a loop for all the vertices. Now first of all what we have to do, we have to make the set of all the vertices. How we have to make the set? That we have to sort all the edges of E into a non-decreasing order, means from the smallest to the largest one, on the basis of their weights. Then after that we have to choose the minimum weight edge from the given link, and we have to do the set. If we are not having any set between U and V, U and V means U is the first node and V is the next node, then what we have to do, we have to do the union from U to V, and then after that we have to again return to the A. So this is the way how you have to talk about the Kruskals algorithm. Now you can check an example also. Now I have taken the same example which I have taken in a Prim's algorithm. So we will get the similar graph by using the Kruskals algorithm. Now you can see the example. In this example, what is the first step? That we have to remove all the loops, cycle loops as well as parallel edges. So in this graph, if we remove, so we have to remove 9 as well as 1. So finally we have this graph as a minimum cost least associated graph, so that we can use this graph. Now you can see the example of Kruskals algorithm. Suppose this graph is being given. So what we have to do, we have to first of all make a forest tree. So for this graph, I will make a forest tree, that S, A, B, then we have T, then we have D and C. Now you can see similarly in the given graph, I have covered all the vertices, right? So after that, first of all, we have to create the forest of a tree. So this tree is called as forest tree. Fine. After creating the forest tree, what we have to do, the second step says that we have to arrange all the edges in their increasing order of their weight. So from this graph, you can check that the minimum weight is 2 between B, D and D, T. So you can see, first of all, we have write the cost of 2, 2, 3, 3, 4, 5, 6, 7 and 8. This is the way how we have to arrange the given weights. Then after that, what we have to do, first of all, we have to add that edge which is having a least weightage. So suppose if we have already arranged in an increasing order, so we know that B, D and D, T is having the same weight. So we can first of all check, because there is no node connectivity, so we can add both the edges. So B to D, we are having a weight 2 and D to D is 2. Fine. So similarly, this way you have to add these two edges. So in this graph, we have making highlighting to both the edges. Then after that, again we have to choose the next minimum weight edge. If the next cost is 3, you can see the table also, the next cost is A to C and C, D. So it means in both the cases we are having the weights 3, 3. Now you can see the graph. If I'm talking about A to C, it is having a 3, so it is not yet connected because our graph is in this form. And simultaneously between C to D, again it is also not connected, so we can write this graph also. Fine. Then after that, from the same table, you can check the next weight is CB, that is 4. So we have to check in the given graph CB, that is 4. If we join this edge, now you can see it makes a triangle. So that's why we'll not consider this edge. So you can see I'm using by the dotted line. Then after that, what is the minimum weight? The minimum weight is 5. Now again, in the case of 5, if we use this edge as a 5, again it will make a closed loop. So again we will not use this circuit because it will create a circuit by adding this edge. The next is 6. In the case of 6, what we have to do? Again we have to check this also will not be included because it will create a loop. Fine. And finally we have to talk about 7. In the case of 7, that is SA. Now you can see if we include, yes, we can easily do the connection between S and A. So now you can see the things that comes out to be S and A also. Fine. And in the last example, you can check the last edge, that is a 8 weight. Fine. So in the case of 8, if we include 8 here, right, S to C, so it means in this case what happened? It will use closed loop or a cycle. So what we have to do? We will not add included. Now you can see in the case of prims also we are getting the same graph or the same minimum tree, and by using the Kruskals also we are getting the same tree. So what happens? Now we have to again calculate the cost of this tree, but by using the Kruskals algorithm. So what is the minimum spanning tree? That is 7 plus 3 plus 3 plus 2 plus 2. Now what happened? After doing the calculation of this, we are also getting the same weight, that is 17. Fine. So we can say either we are using a Kruskals algorithm or Prim's algorithm. We always get the same result by using the minimum spanning tree because these are the two different approaches but doing the same work. So we can say this is called as a Kruskals algorithm. So after that, if I'm talking about its runtime also, so its complexity is also similar, that is E log V. Fine. Now in both the cases you can check that we are getting the same minimum spanning tree, but there are the two different ways to do the minimum spanning tree. Thank you.